Alrighty, welcome to my favorite part of chemistry. I love organic chemistry. It's very different from inorganic chem or general chem that we've been doing this whole year. If you pursue a degree in the sciences, if you go on and get a biology degree or a chemistry degree, or you want to be some kind of doctor, you will have to take a whole year on organic chemistry. And I was afraid of OChem because I heard from people that it was this scary monster. But in fact, it was delightful. I loved organic chemistry. It almost made me become a chem major as opposed to a bio major, but it didn't. But it's great. I like it because it's more about shapes and it's more about things that you can picture and draw than it is about math and kind of abstract concepts. So it's much more concrete. I liked it a lot. I hope you enjoy it too. This is an introduction to a whole new world of organic chemistry. Okay. Thank you for the song. Yes. So organic chemistry is the study of covalently bonded carbon compounds. So we know what covalently bonded means. We know what carbon is. So this is carbon sharing electrons with other things, most often with other carbons. This is carbon-carbon bonds most of the time. There's a lot of hydrogen in these things too. And so they call the kinds of molecules that we're dealing with hydrocarbons because most of the time, most of the elements are hydrogen and carbon. Okay, so hydrocarbons. They form very large, stable, non-polar molecules. So there are some exceptions to the non-polar part, but most of the time, hydrogen and carbon form big non-polar molecules. So this is where we get all of the biology chemistry. So all of the proteins and the carbohydrates and the lipids and the nucleic acids, these are all kinds of organic chemistry molecules, okay? And these molecules are huge. So these aren't small little things that you can easily do a Lewis structure for. Most of the time, biomolecules, organic molecules are monstrous. They're very, very, very large. And so if you were to be assigned to draw a Lewis structure of, a protein, it would take you months to get it done properly. And so these are very large things. The principal elements involved in organic chemistry is carbon. Most of the time, most of the elements is carbon. It's most of organic chemistry. Matter of fact, if something does not have covalently bonded carbon in it, then it's not an organic molecule, and organic chemistry does not apply to it. Okay, so covalently bonded covalently bonded carbon is the principal feature of organic chemistry. Okay, carbon makes 4 covalent bonds. You already know that. Nitrogen is another thing that you're going to see a lot of. Nitrogen makes 3 covalent bonds. Oxygen makes 2 covalent bonds. Hydrogen, or any halide, will make 1 covalent bond. And so these are the things that you will see. Carbon, nitrogen, oxygen, hydrogen, and occasionally a halide. There are some exceptions. Sometimes you see phosphorus, sometimes you see sulfur, but most of the time it's these 5 things, okay, that you're going to see in a big organic molecule. So I'll give you a moment to write that down. It's a lot of text. Okay, so the main way to express an arrangement of an organic molecule is with a structural formula that shows the bonds between the atoms, and I'll show you some examples of this. So because organic chemistry is almost all carbon, hydrogen, oxygen, nitrogen, and sometimes halides, you wouldn't learn much from just writing out like C394, H412, O16, and 12. Like, if you wrote that out, you would have no idea where to begin to arrange this. What does this look like? How does it, how is it put together? How would I begin to do a Lewis structure for it? You would have no idea. And there would be tons of Lewis structures you could draw off of that empirical formula that would be different than your neighbor, who could also draw a good Lewis structure off of that empirical formula. And so the just straight, here's the elements and here's how many of them there are, is not very helpful. And so we want to show how it's arranged, and we use a structural formula to do that. And so it shows how the elements are bonded together. And then there are still lots of ways that you can put the same structural units together to make an organic molecule. So we talked about isotopes a while ago. An isotope is an atom that has the same characteristics because it's the same element as another atom, but it has a different mass, it's got a different amount of neutrons, and it has some slightly different personality quirks because of that. And the isotope, iso means same as or similar to, right? And so isotope has to do with it being the same elements, but not quite the same, because it's a little bit different. Here we have the same word here for isomer. Mer has to do with structure or unit or how it's built. And so this is a similar building, a similar structure. Structural isomers have the same elements in them, but their elements are arranged differently. So it might have a 4-carbon chain of all 4 carbons in a line, or you could take the last carbon and stick it as a side branch, and then you'd have 1 carbon in the middle and 1, 2, 3 carbons around it. Well, they'd both be C4, but very different behavior in chemistry. And so those two things would be structural isomers. They are related to each other. They have the same formula, but they behave differently because it's been arranged differently in the molecule. Often a carbon with its hydrogens are written as a unit. And so you will frequently see CH3 or CH2 showing up in the formula. And it might say CH2, 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 and then something else. And you're like, well, why didn't it just say C3H6? Well, because C3H6 you can put together lots of different ways. But if you see CH2, you know that there's a carbon that has a hydrogen and hydrogen, and it's bonded to other things. And so that unit lets you know that that's all one, like, pearl of the necklace. That's all one unit of the string. So they'll write a carbon and its hydrogens together as a thing, and then they'll write however many of those there are to help you understand how it's put together. Also, hydrogens may be omitted and assumed as existing at the end of drawn bonds. So you can draw a picture of an organic molecule, and they don't draw all the hydrogen on there. They will draw bonds to carbon, oxygen, nitrogen, halides, other things. And then when you look at it, you just know that there's a lot of hydrogen around the edges because there's tons of hydrogen in an organic molecule. If you were to draw all the hydrogen, sometimes it gets cluttered. So they will just draw the things that aren't hydrogen, and then you know that the hydrogen has been stuck on the edges there. Okay? And then rarely carbons are assumed and are omitted too. So sometimes you can see structural formulas drawn out, and you'll just see lines, and they won't put C's in. And if they don't put another element, it's a C, because there's mostly carbon. So I'll show you pictures of this in a minute. Assumed at nodes and omitted. So they don't actually put all the letters in. They'll draw an N, an O, a P, an S, if it's something other than a carbon. But they won't put C's everywhere, again, just to try to keep it clean and easy to read. So let me show you some pictures of this. This is an organic molecule because it has covalently bonded carbon. It has 3 carbons, right? And that's the central backbone of it, but every carbon will make 4 bonds. So it has 1, 2, 3 hydrogens off of this carbon. It has a hydrogen and a bromine off of this carbon, and then again 2 hydrogens and a chlorine off of this. So you could name this. This is ethane because it has, this is propane because it has 3 carbons. You'll learn the naming rules in a little bit. And it has hydrogens. We don't have to worry about naming that, but we would want to tell somebody that it has a bromine and a chlorine. So this would be something like chlorobromopropane, something of that nature, right? And so the formula here tells you how it's arranged. We don't have to always draw all of the groups. So sometimes you'll see O and then C, and we just can assume that there's a single bond between here if it doesn't tell us any different. And then CH3, again, it's a carbon with a hydrogen at the other three positions. And they'll just put CH3 there as opposed to drawing all the bonds again to try to keep it clean and help you see it more clearly. So CH3 on one side, and then they'll write it the other direction here, H3C, to let you know that the oxygen is bound to the carbon, and the carbon then to 3 hydrogens. Okay, so they're helping you see how it's arranged. And notice they only drew bonds for the thing that is different, the sulfur double bonded to an oxygen. They want to make sure you know that. So they'll draw that part, and they'll just like write letters for the rest. Okay, here's another example. Now here they didn't write the C's in at all. They just are letting you assume that all of these junctions, all of these nodes are a carbon. And if they don't tell you something different, it's a carbon. So carbon double bonded to an oxygen, a single bonded to another oxygen. And then carbons here, 6 of them, with an alternating single and double bond. So this carbon has a double bond to this carbon and a single bond to this one. And then this one has a double bond to this one, and this one has a single bond and then a double bond. And wherever they don't put a letter, it's carbon. And then also, all these carbons have 4 bonds, but there's only 3 at each node, right? 1, 2, 3. So there is a 4th bond to the carbon, and it's a hydrogen, and they didn't draw it. But there's a hydrogen here, and a hydrogen here, and a hydrogen here, and a hydrogen here. And again, to try to keep it simple and clean and let you see the essence of the molecule, they omit the hydrogens and they didn't draw the letter C, so that what stands out to you when you look at this is, oh, it's the alternating double bonds, right? That's what they wanted you to get from the picture. Here are 3 ways to show the same thing, and you'll see this in your book. This is what we just saw, a 6-member carbon ring with alternating double bonds. You can draw that this way too. It looks like a nut. And what it's showing you is that these bonds can actually flip around. Like this double bond can migrate over here, and then that will force this double bond down, and that'll force this double bond over. And these double bonds can flip around. And so because of that, sometimes you'll see a circle drawn showing that these 6 carbons are sharing alternating double bonds, but I'm not sure where they are at any given moment. And then this means the same thing. This says these 6 carbons are sharing alternating double bonds, and it's kind of distributed around the ring. Okay, so sometimes you'll see it drawn differently. But these are all examples of a 6-member carbon ring with alternating double bonds. Take a second, write this down. Okay, 2 families of these molecules. The aliphatics and the aromatics. Aliphatics are organic molecules that are either straight chains, or they can be branch chains, or they can be rings, but they're almost all single bonds. There are some double bonds in there, but it's not a overwhelmingly double bonded kind of structure. An aromatic, though, is like what I just showed you, a ring of carbon where they're distributing this alternating double bond around throughout the molecule. And the reason that we draw it sometimes with the circle or the dotted circle in the middle is because the valence electrons aren't necessarily associated with one carbon atom. When the carbon gets into this kind of arrangement, it shares the electrons diffusely around the carbon, kind of like metals do. And so they're called aromatics. What do you think of when you see the name aromatic? What comes to mind? Aroma, smells, right? And these molecules part of what happens when carbon gets into that structure is it gets a very low boiling point, which means these molecules vaporize quickly. They become fumes very, very readily. And so sometimes that's good because we can use these to make perfumes. Sometimes it's bad because the fumes happen to be toxic and can cause problems. But aromatics vaporize quickly. That's something that you'll discover in organic chemistry. And when you open a container of an aromatic, you'll immediately smell it. But if you open a bottle of aliphatic organic compounds, you've got to like waft it towards you and maybe heat it up a little bit before it starts to give off vapors. Okay, so yeah, aliphatics and aromatics. Those are the two like broad categories. Some other terminology that we use, we name molecules based on how many double bonds or triple bonds there are. If there are no double bonds anywhere in the molecule, it's all single bonds, then it fits into a category called an alkane, and the A-N-E part of that word is going to go into the naming of that molecule. So propane is called propane because it has no double bonds. Okay? Butane is called butane because it has no double bonds. Methane, no double bonds. Okay? Octane, no double bonds. Anytime you see A-N-E, it means it's no double bonds in that molecule. It's all single bonds. And then we also use the word saturated when we talk about alkanes. And this is more of a nutrition thing. To say that a fat is saturated, a saturated fat, is a organic molecule that is in the category of lipids and has no double bonds anywhere. Well, the reason that's a problem for your body is because your metabolism starts digesting a fat at a double bond. It's like that's the beginning place for breaking it down. So if you eat something with saturated fat and you eat unsaturated fats, your body is going to digest the unsaturated fats first because there's a place to start breaking down the fat molecule. And when it gets to a saturated fat, it's going to be like, oh, that's too hard. I'll set that aside for later. Which is why the saturated fat is what makes you fat, and the saturated fat is what adds to your cholesterol. Because your body's like, that's too hard. I'm not gonna try to break that down right now. And your body only digests the saturated fats when you are seriously losing weight and you run out of all the easy to break down fats. Then your body's like, okay, I guess I've got to go to the difficult category and start taking apart these saturated fat molecules. Right? So alkanes are hydrocarbons with no double bonds. If it is a fat, and if we're talking about food, then we use the word saturated to describe an alkane. Okay, fewer active sites, harder to get to them to react. They mostly just sit there, and so they're very stable and they're very boring as far as chemistry goes. And your body thinks so too, which is why it hangs on to them until the last resort. It's the famine food for your body. Okay, here's some pictures. Ethane is here, 2 carbons, 6 hydrogens, a single bond between the carbons, and so that is an ane, an alkane, no double bonds. This is propane, no double bonds. And the prefix, you're probably already figuring out, the prefix has to do with how many carbons there are, and the suffix has to do with the kinds of bonds. Okay, so ethane, eth means 2, prop means 3, but means 4. Okay, and you'll learn this as we go. So we name things based on the kinds of double bonds and how many carbons there are. Okay, I'll take a second to write this down. So alkanes, no double bonds, saturated. Alkenes, so the only difference in the word is the A versus the E. And then in the next group, a Y, right? Alkane, alkane, alkene, alkyne. Alkenes have at least 1 double bond in the molecule. So it may have 100 carbons, but if there's at least 1 double bond between those 2 carbons somewhere, then it's no longer an alkane, it's an alkene. Okay, And so this would be an unsaturated because you could potentially put more hydrogen on there. There's some place where there's only CH instead of CH2. And so we call it unsaturated because you could add more hydrogen to it if you could break that double bond up. If it's a fat, these are the kinds of fats that your body knows where to start digesting it. It attacks the double bond and then goes from there. Alkynes are hydrocarbons that have at least one triple bond. Okay, so just like an alkene, it's also unsaturated because you can add more hydrogen to it at some point. And these are the most reactive of the organic molecules. These are the ones where chemistry can mess with that triple bond and get energy out of there or get reaction sites out of there to do something. So propane you can burn for a fuel, but that's one level of energy. Propene would be 3 carbons with at least one double bond, and that has more energy when you burn it. Propyne would be 3 carbons and then 2 of those carbons having a triple bond, and that would release even more energy. Matter of fact, acetylene torches, you guys have heard of acetylene torches, right? Acetylene is the common name for it, but acetylene is actually ethine is what it would be called if you were to name it properly. 2 carbons, a triple bond, and then 1 hydrogen hanging out of each side. And acetylene is incredibly hot when you get it to burn because you're breaking up that triple bond. So these are the 3 suffixes to how we name organic compounds. Ane, ene, and ine will tell you does it have any double bonds or does it not. Where's my mouse? So here's some just examples. Ethene, eth means 2, and ene means a double bond. So 2 carbons with a double bond. Propene, 3 carbons with a double bond. So prop means 3, you'll learn that in a minute, and ene means at least 1 double bond. Bute means 4, ene means at least 1 double bond. Now you don't know where it is. Butene, if that's all it tells you, then it could be here or here or here, because all you know is there's 4 carbons and at least one of them has a double bond. We'll get to more detailed naming rules in a little bit. But butene would be 4 carbons with at least 1 double bond. And then this is a picture of what a double bond actually is. A double bond is 2 electron orbitals being shared end to end, and then 2 electron orbitals being shared above or below the molecule. And so that's what a double bond actually is this pair of electrons being shared straight across, and then another pair of electrons being shared above and below the bond angle. And so they call those a sigma bond and a pi bond. Don't get too stressed out about that. We'll get into that more later on. Here's more examples of double and triple bonds. Here we have a carbon and a carbon that have been joined by a triple bond. They're sharing 6 electrons between the 2 of them. It's a very high energy bond, okay? And so because there are 1, 2, 3 carbons, and because there's a triple bond, this is propyne, okay? This is how it would look in a structural formula, where you have carbon, carbon, and then a triple bond to another carbon. And this is what the electrons look like when atoms covalently share 3 pairs. Again, there's the pair of electrons being shared end to end. Then there's the pair of electrons being shared above and below. And then there's a pair of electrons being shared left and right. And so here we have 1, 2, 3 pairs of electrons being shared across this thing. And sometimes it's just drawn as a cylinder because there's so many electrons above and below and left and right that it's just drawn as a cylinder, this mass of electronegativity here that the atoms are sharing. Okay? So ane, ene, and ine. So again, we named these things based on how many carbons there are. We named them with the longest possible chain. So if something is branched and there's a 2-carbon segment and a 3-carbon segment and a 4-carbon segment, we wouldn't go the 2-carbon and the 4-carbon and say it's 6 carbons. We would go the 3-carbon and the 4-carbon and say it's 7 carbons. So we take the longest possible road through the molecule and we name it based on how many carbons that is. Okay? There's a roughly from the Greek language, although not all of them are, list of prefixes that you need to memorize. Okay? It's table 18-2, and again, this is last year's page number. It's page 461 in the current chemistry book. And that is going to give you all the prefixes. So 1 is meth, 2 is eth, 3 is prop, and then bute, and then pent, and then hex, and hept, oct, non, and dec. And so you'll get that on the table. You do need to know that. And so you've got to learn to count to 10 in the language of chemistry. And when you have the longest carbon chain in the molecule, that's the prefix. And then the second half of the word is, are there any double bonds? Are there any triple bonds? So the example I gave here, propane, 3 carbon bonds, 3 carbons, all single bonds, propane. Okay, 4 carbons with 1 double bond in there somewhere, butene. 5 carbons with 1 triple bond in there somewhere, pentyne. Okay, and so you'll get familiar with how to do that. It's not hard. Prefix, how many carbons? Suffix, are there any multiple bonds in there? Okay, and so become friends with table 18-2. Here we're going to just practice a little bit. So 1, 2, 3, 4 carbons with no double bonds. So this 4 is bute, and so this is butane. Okay, 1, 2, 3, 4, butane. Don't worry about the extra group on the side yet. We'll get to that later. Here is 1, 2, 3, 4, 5, 6, 7 carbons, no double bonds. 7 in this new language of chemistry is hept. So what would this be? Heptane. Yes, no double bonds. Heptane. Okay. 1, 2, 3, 4, 5 carbons in the longest chain. 5 is pent, so this is pentane. Yes, pentane. And that's the end of the examples, but we will get through lots more. So this is the introduction to organic chemistry. It's a lot like geometry. So it's about structure, physical objects. How is the physical object arranged? Okay, that's what organic chemistry is. Anybody have any questions? God bless you.